All right, just allowing the room to fill up a little bit more. Okay. Hello, everyone. My name is Saray Edwards. I'm a marketing and communication specialist at New Buildings Institute, and I want to welcome you to our Sizzling Solutions, Accelerating Heat Mitigation Policies, Programs, and Design Dynamics. Today's webinar is being recorded. You will receive a link to the recording and presentation slides once it's over as a follow-up. You can share your thoughts by chatting to everyone. You can also click on the chat again to hide chats if you find it too distracting. Feel free to respond if you know the answers to any questions that appear in the chat. And speaking of Q&As, there will be time for questions at the end of our time together. So go ahead and put your questions in the Q&A section as they come so we can find them easily and respond. I will be on hand in case you have any technical issues that need fixing, as well as any additional support. And with those words said, I would like to pass the microphone to Liepa, our moderator of this webinar.
Great, thanks, Surya. Can we start sharing our presentation? And meanwhile, hello everyone. Welcome to today's webinar on Sizzling Solutions, Accelerating Heat Mitigation Policies, Programs, and Design Dynamics. The cumulative effects of extreme heat and urban heat islands are making our cities less safe while increasing air pollution, energy consumption, and greenhouse gas emissions. What can jurisdictions and building designers do to combat these issues? Over the next hour, we will hear from speakers on ways to mitigate urban heat islands and extreme heat. And this webinar is co-hosted by both NBI and the Cool Roof Rating Council.
One moment, please, Leipa.
Yeah.
Soraya, I don't see the slides. It looks like they're coming up now. There we go. And if you could put those into presentation mode, please.
Perfect, thank you. So I'll get going with introducing our speakers today. With us today is Audrey McGarrell, Project Manager of the Cool Roof Rating Council, a 501c3 nonprofit organization that brings objective scientific information related to cool surfaces. And they bring it to inform decisions about the impacts of heat islands, extreme heat, and energy use in the built environment. Audrey oversees the CRC's Technical Committee and the Wall Rating Program Committee. And in this webinar, Audrey will describe the benefits of UHI mitigation, the material evaluation, and the market availability of cool roof and cool wall products, in addition to the role of third-party ratings in policy and program development, compliance, and enforcement. We also have Shamini Larson, who is an experienced architect working in the architectural and engineering industry for over 20 years. She manages a Salt Lake and Denver-based team of architects, engineers, and technical experts focused on high-performance enclosure design and construction at Morrison Hershfield, now Stantec. She will talk about some of the misconceptions about cool roofs and several design considerations for proper implementation of cool roofs. We also have Danya Iyas, who is the Extreme Heat Mitigation Strategy Specialist in King County's Washington's Executive Climate Office. Her current role is centered around developing a heat mitigation strategy for King County and its local partners, set to be released in the summer of 2024. Danya will describe the observed and projected impacts of extreme heat in King County, and she will provide an overview of the extreme heat mitigation strategy. Lastly, my name is Liepa Bracilite, and I'm a project analyst of codes and policy at New Buildings Institute. I co-lead NBI's urban heat island work and have co-authored NBI's urban heat island and extreme heat code overlay, which can be used as a resource for jurisdictions looking to implement UHI mitigation strategies. In this webinar, I will describe existing UHI policies in jurisdictions around. I will also summarize the measures published in the extreme heat code overlay. Next slide. In today's webinar, we'll provide an introduction to urban heat island and extreme heat, Audrey will give an overview of cool surfaces. Shamini will describe cool roof best practices. I will talk about extreme heat and UHI mitigation in code and policy, and Danya will discuss policy implementation in local government. Next slide. And here at NBI, we advance best practices, codes, and policies through market leadership, research, guidance, and technical advocacy towards a built environment that equitably delivers community benefits and climate solutions. There are three main program areas at NBI, which include codes and policy, building innovation, and leadership and market development. We also wanted to acknowledge our funders, Bar Foundation and the Clean Cooling Collaborative, an initiative of ClimateWorks Foundation, which helped make this webinar possible. Next slide. And just a note, it's still not in presentation mode, if that's a possibility to change that. So going into urban heat islands. Urban areas are particularly susceptible to the cumulative effects of extreme heat and the urban heat island effect. Cities have dense buildings, dark-colored roofs, asphalt-covered roads, and a lack of vegetation. These factors lead to increased absorption of the sun's heat and can raise urban temperatures 5 to 9 degrees higher than surrounding rural areas, though differences as high as even 22 degrees Fahrenheit have been recorded. Next slide. Yeah, thank you. As you may have heard from news coverage, 2023 was the hottest year on record, and 2024 is expected to surpass it. Heat brings along an increased risk of heat illness and heat stroke, and can even be fatal if adequate measures are not taken quickly. The number of fatalities from heat from 2022 and from the past 10 years and from the past 30 years was higher than any other weather event, as you can see in this graph from the National Weather Service. It is significantly more dangerous than cold, but currently our local and national policies don't yet reflect that. Next slide. So in addition to causing heat illnesses, heat has many other impacts to health. For example, many common medications, such as for blood pressure and diabetes and others, those medications reduce the body's ability to cool off. On the other hand, some medications are less effective at high temperatures. And also high heat can increase mental health problems such as depression, anxiety, and can also reduce concentration and has the potential to increase violence. Next slide. Urban heat islands and extreme heat have many other wide-reaching impacts on communities outside of health. High temperatures increase the production of smog and air pollution. Extreme heat also increases energy consumption of cooling, increasing greenhouse gas emissions and utility bills for residents. Also, extremely high temperatures increase the wear and tear of buildings and pavements due to more extreme temperature fluctuation. Next slide. In this webinar, we will discuss the following extreme heat and UHI mitigation strategies. These will include cool roofs and green roofs, cool walls, cool and permeable pavements, shading, trees and vegetation, and a maximum indoor temperature set point, which is basically mandatory cooling. It's important to note that UHI and extreme heat mitigation are both climate adaptation and climate mitigation strategies, since they protect people from extreme heat while reducing the amount of heat being trapped in the atmosphere that exacerbates global warming. And with that, I'll pass on the mic to Audrey McGarrell, who will talk about cool roof ratings and products available in the market.
Thanks, Liepa. Hi, everyone. I'm Audrey. I'm the project manager with the Cool Roof Rating Council. Like Liepa said, I'm going to give an introduction about what cool roofs and cool exterior walls are, how they can help mitigate urban heat, and talk a little bit about the testing and evaluation, as well as availability of data related to these types of products. Next slide, please. So what exactly is a cool roof or a cool exterior wall? These are building exterior surfaces that highly reflect sunlight and emit absorbed heat. We measure how cool a surface is using two different radiative properties. The first of these is solar reflectance, or SR, Solar reflectance is the fraction of solar energy that is reflected by a surface, and thermal emittance is the relative ability of a material to re-radiate heat that is absorbed. Both of these properties are measured on a scale from 0 to 1, where 1 is 100% reflective or 100% emissive. Next slide, please. Another term you may have heard of in relation to cool roofs is solar reflectance index, or SRI. This is actually a calculated value that combines these two measured properties of solar reflectance and thermal emittance into one number that's typically on a scale from 0 to 100. 100 would be a cooler product. In some cases, you can actually have an SRI that exceeds 100. That would generally be if the product has an exceptionally high solar reflectance. I do want to point out that SRI is commonly used for roofing materials, but it is not applicable for exterior wall materials. This is due to nuances with how SRI values are calculated and certain assumptions that go into that calculation. Next slide. So moving on to the impacts of cool roofs and cool exterior walls. I have this divided up by individual building impacts, and then we'll talk about impacts on entire communities, and finally looking at it from a global lens. First of all, cool roofs and walls reduce the surface temperature of buildings and the resulting solar heat gain of the building. This can help reduce the cooling load of buildings that are air conditioned during hot weather, which in turn helps to decrease AC use and lower utility bills, and can also extend the life of HVAC equipment if it's being used less. In buildings that don't have air conditioning or have poor insulation, cool roofs and walls can also help increase occupant comfort and safety. Like Liepa was talking about, heat can have very difficult impacts on people's health. And so in situations where AC isn't available, also like a power outage, cool roofs and walls can make a big difference. I do want to note that all of these impacts can vary depending on a lot of different characteristics of the building. Obviously, things like climate zone, time of year, energy use patterns, even how the materials are installed, can have an impact on the sort of magnitude of the impacts of cool roofs and walls. Next slide. Looking at the community level, the reductions in air conditioning use associated with cool roofs and walls can help improve grid stability, especially during peak times of day and peak seasons. It can also improve air quality by lowering outdoor temperatures, which can improve air circulation as well as decrease in the production of ground level ozone. Reductions to the UHI effect and its associated public health risks from heat waves are also a benefit of cool exterior walls and cool roofs. Next slide. Finally, looking at this from a global lens, installing cool roofs and cool exterior walls actually raises the global albedo, which can help reduce global warming. Furthermore, the reductions in AC use from using these surfaces can reduce the amount of CO2 and other greenhouse gas emissions associated with fossil fuel generated electricity for AC. Next slide. So now we're going to switch gears a little bit and talk about measuring and evaluating the radiative properties of exterior wall and roofing materials. Both of these properties, solar reflectance and thermal emittance, can be measured in accordance with various ASTM standards and other industry vetted test methods at laboratories across the United States and abroad. The most common test method that's used for solar reflectance is ASTM C1549. This is obviously an ASTM standard that uses a portable solar reflectometer to perform measurements on specimens. I do want to mention that while this test method is used for both roofing and wall products, there is a different setting that is required for wall products because of the nuances with how solar radiation is hitting vertical surfaces as compared to low and steep slope roofs. I see a question in the chat. Please define ASTM. ASTM is a standards organization that develops and maintains standard test methods and specifications for different building products and all kinds of other products. So they're a global standards organization. Moving on to thermal emittance, the most common test method that's used is referred to as the slide method. This is not an ASTM standard, but it's an industry vetted adaptation of ASTM standard C1371. This test method was developed in order to provide more accurate measurements of specimens that have low thermal conductivity. So basically, most roofing and exterior wall materials, aside from metal, tend to hold on to heat. They don't conduct it very well. And so that can affect the thermal emittance measurements. So this method is a way to get more accurate results for that type of material. We can go ahead and move on. Another really important part of evaluating a material's radiative properties is natural weathering. So the industry standard for natural weathering is 3 years, a period of 3 years of natural exposure. And for the CRC's rating programs, which I'll discuss in a moment, we require specimens to be exposed in 3 different locations: Ohio, Arizona, and Florida. Natural weathering and then following up with aged testing is a great way to sort of get an estimate of how a product will perform over time, since obviously once it's installed on a building, things like UV radiation, soiling, etc., will have an impact on the radiative properties. Next slide. Something else that's available for roofing products only is laboratory aging to provide simulated aged values. This is important because certain building codes require an aged solar reflectance value when installing a roof. So if a product has just recently been tested, this is a way to get that aged value and to work towards code compliance without having to wait for 3 years. When aged values become available, they do replace the laboratory aged values. Next slide. One common question is whether cool roofs and walls are only white. While white roofs are one very common and easy way to achieve a high solar reflectance, they're not the only option. There are many roofing and exterior wall products that are available using materials that reflect infrared radiation while maintaining a darker visible color. A few common examples would be factory-coated metal roofs and siding. There are asphalt shingles that are made with infrared reflective granules. There are also a variety of paints and coatings for both roofs and walls that utilize this type of technology. Next slide. This on screen here is just an example of what I was just talking about. I'd like to call your attention to the 2 different black tiles on the far left. On the top row, that is what we call a cool color that uses infrared reflective pigments. And on the bottom is more of a conventional black. As you can see by the numbers on screen, the cool black is 10 times more solar reflective than the conventional black. Moving on, I want to briefly mention the existence of the CRC's rated products directories. These are available online and they offer free publicly available roofing and exterior wall product solar reflectance and thermal emittance ratings. Our ratings include both the initial values, so those are the properties that are measured initially when the product is brand new, and then the aged values, which occur after that 3 years of weathering. The data are obtained following following industry vetted test methods, like I said earlier, and also by independent accredited laboratories. So this provides assurance that the data are credible, they're unbiased, and the specimens are also managed under a strict chain of custody. And all of this testing is done in accordance with our proprietary program manuals, and for our roof program, in accordance with the ANSI CRC S100 standard. That is an American national standard that is maintained by the CRC. And it's actually referenced in a lot of codes, programs, and standards that promote the use of cool roofs. Last slide, please. So finally, to tie this into today's topic, third-party ratings have an important role in policy and program development, compliance, and enforcement. Like I said, they provide assurance that data are accurate, and they help bolster claims being made by manufacturers or people selling cool roofing and wall materials. They also can help support the development of policies and programs by providing a repository of data to reference to see, if a policymaker is evaluating policy options, whether or not there are products out there on the market that can be used to comply. So that does it for my portion, and I will turn it over to Shamini to talk about installation.
Great. Are we ready to go? I think there was an attempt to change the slides. No? You're good? Okay. So I think there are some essential concepts that are important for creating resilient design in roof systems. And I don't know if you can see in the background here, but there is a building back there that has a planted roof. And I would say, urban heat island is important for not just urban areas, but also rural areas. This is a project. It's the golf maintenance building for Park City's municipal golf course. And in this photo, you may not be able to see, but there is a planted roof that kind of integrates this roof into the landscape. And you may want to integrate a cool roof for a lot of reasons. It may be relative to urban heat island. It may also be, to help preserve, snowpack. A lot of different things could be beneficial for designing a cool and resilient roof. Next slide. So a good roof really does mean a good building. And I think any designer, that's worked on buildings knows that if you have a roof that doesn't perform, it really can snowball into a lot of problems with your building in terms of material degradation and a lot of issues. So there's obviously a good roof has the potential to reduce thermal expansion in structural components. And so all the structure kind of stays where it's supposed to be more often. Less movement and reduced risk of cracking and finishes. A lower risk of condensation. We'll talk about that a little bit more. And obviously, if you have a roof system that works, having a dry building is very sustainable because obviously just buildings that fail and have water intrusion issues have to be replaced. And that's, more materials, more cost, a lot of problems. So I just make the point that a good roof is a good building. Next slide. Common roof assemblies vary. And I think, in 10 minutes, we can't really cover all of the types of roof assemblies there are on the market. There's probably thousands of different UL rated assemblies out there. They all have different types of performance depending on where you're building. But a lot of them have the same basic components, a waterproofing component, an insulation component, some layer that controls air and vapor as well, in addition to the water, and methods that they're secured in order to meet demands for wind uplift and other kinds of forces that are present in whatever climate you might be working on. And so we'll see, the roof is a system, it's an assembly, it's not just one component, and it does have, a specific layering that helps it perform when it's put together properly. Next slide. So best practices for roofs in general are to slope them. Let's get the water off the roof. Let's really think about, one of the primary functions of a roof is to keep moisture and rain and snow and ice from entering the building. They're often multi-layered for added durability. You see a lot of built-up roofs where you're adding layers together to create waterproofing, all those performance aspects. They can also be protected roof membranes where the actual performance layer is located below things like solar panels, or they're below pavers or something like that. And they, really need to be designed to reduce wear and tear. So if you're going to add, a solar array or some kind of planted medium on top of an existing roof or a new roof, you want to understand how those things are going to weather together, make sure that they're all designed to be together for a very long time. We want roofs to last over 20 years. Typically, that's a minimum amount of time that you want a roof to last, but we do often design roofs that last a lot longer, and they can be in place for, up to 50 to 70 years sometimes. So the idea that they can be maintainable and durable over a long period of time is really important. Next slide. So urban heat island and roof systems is, again, a part of designing to achieve a solar reflective index, and that's a code compliant requirement. So again, the range is between 0 and 100 typically for most roof products that you can access in the market. It also applies to LEED sustainable sites, and it is related to the membranes, the metal components, the finished materials, rooftop amenities such as pavers and pools. All those things start to factor into how your roof will actually perform when you think about how it impacts urban heat island. There's also plants and planted roofs that help you reduce the impact you have on an urban heat island, and also help you when you're trying to meet code, develop your methods for compliance. In the photo, you can see that that's in like an ETFE roof. That's basically a pillow of membranes together that sort of support these big long spans. So depending on your project, maybe you have a really traditional roof over something, or maybe you have something where you're trying to span a very big opening. This is a stadium, but you can achieve, very lightweight, light colored roof membranes in multiple different types of membranes across your portfolio of buildings, and maintain that impact on your urban heat island, or reduce your impact on your urban heat island, I guess I should say. Next slide. So roof selection and your solar reflective index should be considering a couple of different things. Obviously, the emissivity and the solar reflectance are important, but you also want to know, how much is my building going to be exposed? Am I in the shade or the sun? And am I on a mountain slope that's on the north face of a mountain slope where we're not going to get a lot of sun? And what is the climate that I'm working in? So all those things start to impact how you're going to pick what kind of roof system that you actually need to perform. And, those climates have a lot to do with, are you in a heating dominated climate or a cooling dominated climate? And how much are you trying to mitigate that urban heat island that's possible on your site? Next slide. So cool roof design approaches. One is obviously to select a product that has that reflectivity that mitigates it. Another one might be a planted roof or some kind of protected membrane roof. Those are two of the most common strategies. A high SRI material may not always be required by code, so it's worth kind of understanding when it's required and why it might be required, so you can design appropriately. A shaded roof area, say you have a roof that's never going to be in the sun at those times, you might consider, is that the appropriate kind of solution to my design problem? Am I going to put it below photovoltaics or some kind of thermal hot water system? Is it a greenhouse and I need to grow food? Obviously, a greenhouse isn't going to have an SRI, higher SRI material potentially. Or is it a cold climate? And I put a question mark there because sometimes cold climates, you still want a high SRI material. But, if you're trying to heat a building often, there may be some cases where, a darker roof color can help you warm that building. And those are usually pretty extremely cold climates where that may make sense. It still may have an impact on urban heat island, and you still may want to reduce that in general. Next slide. So roof color selection matters. This is just a chart from one manufacturer that shows their calculation for energy savings based on both location and a high SRI material. So you can see that in Miami, the potential for energy savings is pretty significant, whereas in Duluth, it may not have as a significant impact on the cost savings that you might see, or maybe just the overall energy savings you might see. So that climate, along with, your selection of roof material, has an impact on how much you potentially can save in terms of energy costs. Next slide, please. So again, just the SRI might be something that you pick based on the solar reflective index. It ranges between 0 and 100. It can be a membrane, and it can also be other components or finished materials. Rooftop amenities or plants may also be a part of that. Next slide. So just some planted roof pros and cons. Pros, I think a lot of people love planted roofs. They're beautiful. They have a lot of benefit in terms of amenities. We tend to love how they look. This is a building, a conference center that has a planted roof on top of it, and you can see it has very tall trees in those plantings. So it has a great benefit of this public amenity or maybe a semi-public amenity potential, and that ability to reduce heat island, create some kind of habitat for plant animals and insects in your community where there may not be a lot of those options otherwise. The cons, you may be considering, is my climate appropriate for this? If you're in a desert climate, you're going to be adding water to your building or actually putting water on top of your building. These places need maintenance and care. They can also obviously cost more upfront. Your roof membrane needs to be protected. So if you have roots growing through your roof assembly, you need to make sure that there is a root barrier or some kind of place where you limit the ability of the root to move through the building materials that you don't want it to move through. And then that leaks may be hard to find. If you have a system like this, it's very much covered up. You may not be able to find some of those leaks after the fact if water's moving laterally in your roof assembly. Next slide. So plant selection is also a really important part of a green roof. You want to obviously make sure you understand the climate that you're working in terms of hardiness zone, rainfall, and wind. You want to understand your site. How much sun and shade will my site actually get? What kind of biodiversity do I want to create with this solution? What size of vegetation do I want? And the visibility as well. Maintenance is also a huge consideration with planted roofs. Do you want to do year-round maintenance? Do you want to allow just sort of whatever the wind brings to the roof to settle and grow there? Or are you going to do a lot of weeding and care to try to maintain a certain set of vegetation that you're looking for? Access is also important. If you have a roof that needs maintenance, you need to make sure that access is safe. And that there are options to access the roof. The picture in the far left or right lower corner is a roof deck, and it has access by the public, which makes it easy, but not all roofs have that, so that maintenance needs to be considered as well. Next slide. Another part of roof assemblies is obviously, controlling other kinds of things that have an impact on maybe the performance or the quality of the building underneath the roof, and air leakage is a big part of that. So most roof assemblies have some level of air control that need to be considered. When we don't control air, we get problems. So the picture on the left is showing, an air leakage test. We have a lot of ways to determine where we have air leakage and how much air leakage is happening at our roof assemblies. And the pictures on the right are what happens when we allow a lot of air maybe to move through our roof systems into a parapet condition in a colder climate where maybe that humidity can land on surfaces and result in some kind of risk of condensation. So controlling air and understanding how air is moving through your roof is also a big important consideration for getting a high quality roof. And this happens in all of the transitions of the building: parapets, penetrations, skylights, drains, any kind of connection point structurally for like a solar array or some kind of landscaping wall has the potential to promote air leakage and have some of these risks. Next slide. Another point I want to make is that in design of roofs, we need to address thermal bridging. And I'm just touching on this, that there are definitely ways where we can design planted walls and green roof walls to have a significant impact on the energy use of the building if done properly. So the slides on the left show a roof assembly with maybe a wall, some kind of parapet wall that extends through the insulation layer, and the color diagram below shows the thermal imaging and model of that that approach for the design. And then the images on the right show another solution where the insulation can run below that wall, and how much that mitigates a lot of that thermal heat flow through the assembly. So some of the amenities and features that make us really like planted roofs and roof amenities also can have a significant impact on the energy use of the building, and designing to mitigate those when it has a significant impact is important. Next slide. Just kind of reiterating this a little bit more, that parapets also have this potential, and I would say any detail really has that potential, but you can see how an uninsulated parapet detail, has the potential to move quite a bit of energy through it. Whereas if the insulation is brought up and over all of these penetrations and is continuous, can have a pretty significant impact on keeping heat in and cold weather out, or vice versa, depending on your climate, just maintaining the comfort of the climate of the building by looking at those roof details a little bit more closely. Next slide. That's it for my portion. Thank you.
Great, thanks, Shamini.
I don't know if there are questions in the chat you want me to answer.
I think we'll go to the questions at the end. We're also, some of us are answering them in the chat, but yeah, we'll focus on them at the end. Next slide. Great. Earlier this month, NBI published the Extreme Heat and Urban Heat Island Code Overlay, which is an overlay of model building code language meant for jurisdictions. The report includes an overview of urban heat island effect and extreme heat, and includes code language for implementing cool roofs, cool walls, cool and permeable pavement, trees and vegetation, and a maximum temperature set point. Next slide. NBI's Extreme Heat UHI Code Overlay report includes code language for several energy codes and standards, including the International Energy Conservation Code and ASHRAE 90.1. The report also includes language for the IGCC, or International Green Construction Code, or ASHRAE 189.1, and it includes language for the International Building Code, International Residential Code, and International Mechanical Code. And since not all jurisdictions have an energy code, and among those that do, building codes are often updated more frequently than energy codes, we added cool roof and cool wall language to the two model building codes. While the model energy codes and standards do include some UHI mitigation strategies already, we moved the strategies from the prescriptive path into the mandatory requirements so that all buildings can benefit from UHI mitigation. We also increased the climate zones of cool roof and cool wall requirements based on research that shows, excuse me, based on research that shows the benefits of cool surfaces exist even in cooler climates. We also added a maximum indoor temperature set point because the building code currently only has a minimum temperature set points to protect people in the winter, but it lacks a maximum set point to protect communities during extreme heat. Jurisdictions can modify this code overlay language in the report and use it for any other policies such as zoning code ordinances, incentive programs, housing codes, and so on. Next slide. The UHI and Extreme Heat Code Overlay report includes code language for 5 different codes and standards. The first type of code is the Energy Code, which includes ASHRAE 90.1 and the IECC, which stands for International Energy Conservation Code. ASHRAE 90.1 is for commercial buildings and multifamily buildings 4 stories and taller, while the IECC includes requirements for both commercial and residential buildings. So as mentioned, both are energy codes, and their goal is to make buildings more efficient. And in the code overlay report, we included language for both cool roofs and cool walls in the energy codes. The second type of code that is included in the report is the Green Code, which is ASHRAE 189.1, also known as IGCC. And the goal of this code is to reduce the environmental impact of buildings. And it includes requirements for cool roofs, cool walls, cool and permeable pavement, and tree shading requirements. And lastly, the third type of code in the report are building codes, which aim to protect the safety and welfare of the building occupants and the public. Codes in this strategy, codes in this category include the International Building Code, International Residential Code, and the Mechanical Code. We included the cool roof and cool wall language in the IBC, in the IRC, and in all three codes, we incorporated a maximum temperature set point. And as mentioned, we included all these code options because different jurisdictions have different priorities. Some really prioritize their energy code, while others work primarily from their building code or their green code. Next slide. So this slide shows just a short excerpt from the code overlay report. It's an excerpt of the cool wall requirement in ASHRAE 90.1. And in the report, any new code language is underlined. So as you can see in the top section, or like the top three text sections of this image, it's all new code language. And then the bottom section is an explanation of the code language of like why we written the way it did, what changes we made, etc. And the language in the code overlay can be modified to best suit a jurisdiction's goals and needs, and it can be used to create policies other than the energy code. Next slide. And next slide. And before a local jurisdiction can decide which extreme heat or UHI mitigation strategy they will implement and the policy pathway they will take, jurisdictional staff need to verify the rights that the state has given to the jurisdictions and what they're allowed to legislate. For example, some states don't allow their cities to create local energy codes that are more stringent than the state code. And in such situations, jurisdictions can implement policies via the zoning code or other strategies. For example, suppose the jurisdiction does not have the power to require cool roofs and walls or any other mitigation strategy. In that case, they can create a performance approach for UHI mitigation that requires buildings to choose a combination of different strategies, but the jurisdiction is not requiring every building to have cool roofs, for example. They can choose whether they want to incorporate shading, trees, cool roofs, cool walls, cool pavement, but there's not one thing that each building needs to incorporate. And there are many different types of policy pathways that a jurisdiction can use to implement extreme heat mitigation. And some of the policy pathways include zoning code, housing code, energy code, building code, incentive program, and others. So zoning codes implement the goals and objectives of a comprehensive plan of a city. They generally dictate function for an area, building height, and bulk, population density, and parking requirements, as an example. Housing codes are a little different from building or energy codes in that they set minimum maintenance standards that must be met by all housing, both new and existing. And they are often referred to as property maintenance codes or sanitation codes. So here's a list of some examples of jurisdictions that have incorporated heat mitigation strategies in various policy pathways. So here, the DC Housing Code requires space cooling during the hot summer months. They require indoor temperatures to be at 78 Fahrenheit or at least 15 degrees Fahrenheit less than the outdoor temperature. The Baltimore Building Code requires cool roofs on low-slope commercial buildings. The Sacramento Zoning Code requires 50% of parking lots to be shaded by trees. The Hawaii Energy Code provides a wall insulation exception for cool roofs. And the Phoenix, Arizona has a cool pavement program where they've implemented cool pavements in over 118 miles of roads. So is just a list of some different ways that different jurisdictions have implemented UHI mitigation strategies. Next slide. Thanks for listening. Please reach out to my email if you have any questions or would like to discuss how your jurisdiction or community can mitigate UHI and extreme heat. And I will now pass the mic on to Danya, who will talk about King County's extreme heat mitigation strategy.
Thank you, Liepa. Hi, everyone. I'm Danya Yaz, the Extreme Heat Mitigation Strategy Specialist for King County. Thank you for having me here today. I'll be talking more about King County's first ever countywide extreme heat mitigation strategy. Next slide. So just to run through a quick agenda, I wanted to talk about the heat strategy background. So why is this important? What exactly we're working on? And then next, I'll be talking about some of the strategy action areas that we're focusing on. And I'll probably be talking less about the technical concepts and explaining more about how we're planning to employ the strategies that the speakers before me did a great job of explaining. And then finally, I'll wrap up for some key takeaways. Next slide. So before getting into what exactly the heat strategy is, I first wanted to talk about how we've observed extreme heat in King County. Next slide, please. So what you're looking at right now is a 2020 heat mapping project with King County, Washington, City of Seattle, as well as a consultant group. So what you see is a snapshot of countywide surface temperatures, and we took 3 different timestamps on a July day in 2020. So what you're looking at right now is the afternoon area-wide temperatures, and the red areas are the higher temperature areas, and you can see that in areas that are more urban in King County, so particularly looking at the south, there's higher temperatures. And if you click one more time, please. On the right over here, I've got the evening snapshot for King County. And so as you can see here, the areas that are considered more urbanized, so again, looking at South King County, which has less impervious surface or more impervious surfaces and less tree canopy coverage, those areas are definitely retaining more heat compared to some of our more rural areas on the east side. But we did find that urban heat really is not the best moniker because there are some areas that are showing up as red, particularly in the northeastern side of King County that are still considered rural, but they're still showing up as heat islands. And when we're looking at this heat island effect, we're noticing that at the evening map, there really is not as much nighttime reprieve from hot temperatures, which can be really dangerous for health conditions. So we're seeing up to a 20 degrees difference between the surface temperatures in those really hot areas that you see in South King County in the red and the more rural, cooler areas. And one more thing to note is that these indoor temperatures can sometimes exceed the outdoor temperatures, and they're the ones that are the most dangerous for health conditions. And we especially saw this during the 2021 Pacific Northwest heat dome, which I'm sure many of you heard about, where we saw over 30 deaths that were directly attributable to extreme heat in King County, which is extremely abnormal for our region. Next slide, please. What I wanted to draw your attention to here is I wanted to juxtapose our evening heat map with an environmental health disparities map. So for the map on the right, the areas that you're seeing in red have higher disparities when it comes to environmental exposure, as well as some socioeconomic factors and some population characteristics that can make people more sensitive to environmental stressors. So for example, underlying health conditions. And you can see that where we see the most environmental health disparities is a pretty direct overlap where we see the most extreme heat in King County. So the people that are the most impacted by extreme heat are some of the most sensitive and vulnerable to it. Next slide. So all of this, along with the 2021 heat dome, formed the impetus for why we wanted to create the first ever county-wide extreme heat mitigation strategy. So it's a priority action in King County's already existing strategic climate action plan underneath climate preparedness and community health. And it's also supported by a FEMA grant as well as additional King County funding. But in terms of our audience, it's not just for King County government. We recognize that as a county of about 2.3 million people, we're a community of communities, each having their own needs and challenges and burdens when it comes to extreme heat. So we are co-developing the strategy with local jurisdiction staff, as well as community organizations and partners to really come up with a portfolio of solutions for what we can collectively do to mitigate extreme heat. And we recognize that this is not really a one-size-fits-all type situation. So the focus here is going to be on a mixture of short-term actions that have more to do with, for example, emergency management coordination, multilingual public health messaging, as well as really getting at some of the systemic factors that affect how people experience extreme heat, such as urban tree canopy management and building codes, and kind of looking at how we design neighborhoods and communities. And the completion date is summer 2024. That's when we'll be releasing the strategy this year. And right now we're working on just really ironing out and refining the actions and drafting them. Next slide. So I wanted to quickly share our draft goal statement just so you understand what our overall goal is with the strategy and what are the strategic priorities that are driving our work. So our goal is to overall reduce the impacts of the harmful impacts of extreme heat on people as well as the environment in King County with 3 different strategic priorities. The first one is going to focus more on kind of that short-term response. So how can we effectively prepare for and respond to extreme heat events when they occur? The second goal is looking at nature-based solutions, so the environment around us, as well as built environment solutions, so the buildings that we inhabit, and seeing how we can develop some solutions that will reduce extreme heat impacts in both indoors and outdoors. And finally, we want to ensure that we're focusing our solutions on the communities that are the most impacted by extreme heat, so our frontline communities. Next slide, please. And now we'll be getting into the action areas. Next slide. So what you're seeing here are draft categories. They're still a work in progress since, like I mentioned, we're still figuring out how many actions are going to be in the strategy and what they're going to look like. But each of these categories that you're seeing here are going to have about 3 to 5 actions within it. And we're at a total of 24 draft actions right now. So I wanted to show the wide variety of actions that we plan to include in the strategy. But if you could click real quick. Thank you. For the talk, we're going to focus on 2 specific categories, which is keeping people safe indoors. So how can we keep people safe in their homes and any other places they may go, for example, cooling centers, and also how we're designing for heat. So essentially, how are we incorporating heat resilience when we're designing neighborhoods and when we're developing or updating new building codes, for example. And I did want to briefly mention that the third category does touch on bolstering urban tree canopy and increasing access to green space, which is kind of similar to what Liepa was mentioning about increasing trees and vegetation, which can also help with cooling. And I'm happy to talk about any of these other categories in the Q&A and offline, but we'll be focusing on 1 and 4 for right now. So next slide, please. So I wanted to start with design for heat because it's the most relevant to this talk. And the most relevant action that we'll be focusing on here is developing and supporting local adoption of a King County building code package that focuses on heat mitigation. And what we're trying to do here is we want to draft model codes and then support local jurisdiction adoption of these model codes. And we're still figuring out what is going to go into this building code package. And a lot of our conversations have been inspired by the amazing work that NBI has done with their heat code overlay. So for a couple of ideas that we've talked about so far is we want to increase the use of high albedo materials in new construction and also for any major retrofits. When we're looking at roofs and increased shade coverage, we're looking at how can we recommend this, as we'd have to attach it to either zoning code requirements or attach it to incentives for local jurisdictions, but figuring out what are some ways that we can really motivate adoption for our local cities. And the last one is promoting best practices in passive cooling. So for example, when we're looking at external operable shading, insulated shades, how exactly can we promote these best practices? And is there a way that we can even have an outreach program with property managers or residents to really underscore the importance of having more passive cooling measures and updating buildings such as multifamily to have more of these different amenities and features. Next slide, please. The next category, helping people stay cool and safe indoors. So I wanted to just really briefly touch on these actions because they do focus on increasing the energy efficiency of residences, as well as reducing financial barriers to active cooling. So the first category that we're looking at is increasing access to home cooling for low-income residents and other vulnerable populations that live in those mapped heat islands that you saw earlier. So the idea here is that we can distribute some passive cooling techniques such as window films or reflective window films that could potentially help reduce solar gain. And we also wanted to focus on expanding heat pump installation programs, since that also supports our greenhouse gas reduction targets as a county. And there is currently a pilot underway to install more heat pumps in low and moderate income homes in unincorporated King County. So that's something we want to support expanding. And the next action is we want to expand access to energy efficient repairs, specifically weatherization programs, as well as utility bill assistance to ensure even if people do need to get portable ACs, for example, they're able to afford these things. Next slide. And what I wanted to do real quick is just really ground it back to community and really talk about what we've heard from our community members and why we're doing this work that we're doing. So we've had multiple community outreach events, and they've all been focused on areas where we see extreme environmental health disparities, as well as mapped heat islands. And we heard that overwhelmingly, even though people say they feel too hot in their homes, they still prefer to stay at home. And you can see that in the survey response that I've got pictured over there on the right. And when we asked them what are some of their major barriers to cooling at home, they mentioned cost as the top one, either purchasing air conditioning, purchasing cooling technologies, and even paying their bills. The second one was difficulty and confusion with cooling options, especially for communities that have limited English proficiency. People cited health concerns, specifically around mobility, and also the concern of power outages. So if they are to get an AC, what if it overloads their electrical system in their building? But overall, we did hear really strong interest from community organizations in increasing cooling capacity of homes and buildings. Next slide. So just to kind of wrap up, I wanted to share some key takeaways, which will be on the next slide. But overall, we heard from folks that people would really prefer to stay at home during heat events. And that just really underscores the importance of that we need to ensure that we're taking extreme heat into account when we're looking at building materials and how we design communities and neighborhoods. Since, like Audrey and Liepa mentioned, higher albedo surfaces can reduce the solar load. And also that can address the issue of cost that people are mentioning, where they'll have to spend less money on, for example, operating cooling technology, like for ACs. And the last key takeaway that I wanted to talk about is that we need a mixture of solutions that look at code amendments, passive and active cooling retrofits, make sure that it integrates with already existing systems. And finally, we want to ensure that we're also communicating all of this. So are we doing outreach in multiple languages? Are we reaching the community members that need it the most? Because all this work that we're doing in built environment is climate work that can make a difference and can save lives. So I know I talked a little fast, so I'm happy to answer any questions offline as well at my email. And I did want to thank my manager, Laura Whiteley-Binder, as well as Kathleen Petrie at King County for their contribution and partnership to these actions. So thank you all so much for your time, and I'll hand it back to Liepa for the conclusion.
Perfect. Thanks, Dania. Yeah, I see that there are a few questions. So we do have a couple minutes for questions. We got 2 questions on PVs and cool roofs. One of them was, could you talk a bit about the compatibility and benefits trade-offs of combining cool roofs with PV solar installations? And the other one, do reflective cool roofs and green roofs have similar benefits to rooftop PV? Does anyone want to take on that question?
I can try to answer it. I'm not an expert on durability of solar PV, but I do know that, you know, they have a tendency to overheat and that can be impacted by the materials around them. And I think there is some level of impact of combining the two there. I do know that, you know, sometimes in solar hot water conditions, you're trying to create reflectivity around the solar collection tubes for like a solar hot water array. So I really think it might be done on a case-by-case basis to understand that. But in general, I think when electrical things get hot, they don't work as well. So in general, I think having a reduction of urban heat around solar arrays is going to be beneficial for the long-term durability of the panels.
Great, thank you. And there's another question from Sasha. Does the energy cost over time slide reflect climate change and shift to hotter and longer summers? I'm assuming that's from Chamonix's presentation.
I'm sure it doesn't. That came from a manufacturer, but it's you know, to be taken with a grain of salt when it's on a manufacturer's website. I recommend, I mean, most of the design information we have, unfortunately, is based on historical data. All of the heating degree day information that we use to decide the loading on buildings is historical. So in general, you know, there's a lot of discussions in the design community. How do you help design for the future? What are we going to use? Where is the best resource for us as designers to say, what will the climate look like in 20 years? And how do I design for that? And does my client want to look at that when maybe code doesn't necessarily have that consideration in mind? Depending on the local jurisdiction, they may be behind several code cycles as well that haven't considered that. So we are starting to have these conversations, and I think they're difficult because they don't necessarily show up in what is compliant from a developer's perspective of what they need to.
Oh, I think we lost Chamonix. All right, and we are at time. I just wanted to conclude that if you have any questions you would like more information on, please feel free to reach out to any of us. And we will be following up to the attendees and the registrants with the slides, the recording, and also the UHI and BI's report. And thank you again for attending. And we hope you have a great rest of your day.